Welcome to the Fire from Two Windows podcast, where we take a deep dive into different aspects of the fire service. My name is Matt Humnicki, and I am joined with my co-host, Lou Caminelli. We want to express that these are our own opinions built by experiences and education while honing our craft. These are not the opinions nor directions from our various employers. We are here on our own to spur conversation and help level the playing field for all. Good afternoon, Lou.
What's up, Matt?
Not much.
So, the one we've been kind of working on for a while started over the summer when we broke out the load cell. I was actually looking back through another email I wrote to some instructors on it. We actually did this back in 2021 where we put the load cell on the aerial with the voice. Pretty much the same. We did a little bit more basic, but we'll get into it right away. So what we're discussing today is what seems to be like the cool thing to do on the internets and the Instagram pages is using your aerial device as artificial high directional. Should you do it? Should you not do it? If you do it, how should you do it? It was a gorgeous Sunday afternoon or Sunday morning whenever we did it, and we were out there for 3 or 4 hours.
Yeah, something like that.
So do we want to just get into what our testing was? I got the write-up right here.
Yeah, let's start right off with that. So
Okay.
You want to preface this. What we were trying to test was we were trying to come up with a way to scale down the forces that are applied to your aerial tip when you load it. So essentially it's going to be, usually the tip of the aerial is used as a artificial high point, but it's usually kind of like more of a change of direction, if you will. And because of that, a lot of people kind of fail to recognize that there is a multiplication force that happens at that tip or on that rung or whatever it is, your attachment point up above. So you want to explain what it was that we established?
Yeah, so after we did it, I kind of wrote a training bulletin up for our department. It was it's pretty lengthy. Most of it was, a lot of pictures and explaining what we did, but I guess you would call it the abstract of what we did. I can read that verbatim.
Yeah,
so it was titled Forces Implied to AHD Artificial High Directional. When using an artificial high directional, there are greater forces created at the change of direction, the COD, than most realize. Using a CMC load enforcer, we conducted 11 different tests and we documented the different forces. These tests were conducted using a 100-pound load. The 100-pound load that we used was 2 45-pound plates plus 1 5-pound weight from our gym at the firehouse. The equipment we used was 11 millimeter CMC Static Pro rope, a CMC Harken clutch, an Arizona Vortex setup, and a monopod configuration. The reason why we used the monopod configuration was to help mimic how an aerial ladder would look. We recorded the angle of hoist, the change of direction of the inside angle, the static load, the max load. We're all recorded every time we conducted the test. We utilized 3 different anchors, which created the three different types of anchors created different change of direction angles. We used a remote anchored at the base of the monopod, and then anchored the clutch right at the top of the monopod. So right inside, there was no change of direction. The descent control device was right at the tip. The angle of hoist refers to the angle at which the monopod was set to. So when we refer to an angle of hoist, that would be the angle that the aerial ladder is at. Roughly, your aerial, depending on your manufacturer, goes from, maybe -5 degrees, -10 degrees, all the way up to usually around 80 something degrees. The interior change of direction angle is the interior angle of which the rope is running through the change of direction pulley. Two separate readings were recorded, static and max. So static force, load just sitting there. Max force is what was the amount of force it implied on the change of direction while the load was moving. Conclusions based off all this tests were at the end of this document, and so on and so forth. I'm going to say right now, if anybody wants this, if they've listened to this, if anybody wants this, contact us at our Instagram or our Gmail account. I'll be more than happy to send this out to you. So I can also read, I went back, this was back done in, I guess at 2022. I misspoke, I said 2021. We also used the CMC load enforcer cell. Load was at 100 pounds. At the time, we were at half-inch static Cormano rope. And I listed off the carabiners that we used. But we can go into the tests that were almost the same, and I'll tell you that the test numbers were relatively the same findings that we knew that were going to happen. So I don't know how you want to dive into this one. We can go test by test. We can talk about the math first and then go into the test and how the test proved the math. Either way, I'm just going to say the finding that I think it just confirmed what we thought here at our firehouse, what was going to happen when we imply rope systems on our aerial ladders.
Yeah, and I think explaining the setup first so that people don't think of, oh, hey, you got all these variables at play that you kind of negated. We tried our best to take out all of the variables. That's why we set up a vortex in a monopod configuration. It's just a straight stick. It's built so that it can be in compression. That's how the vortex works. It's rigid like the aerial, so that what we try to do is make sure that this thing can't sway in any direction that we don't intend it to. We had two guy lines, coming 45 degrees to the rear of the head being an Azorp, which is just a bunch of attachment points at the top. We had another guy line going forward that we ran to the bumper of a pickup truck. And those two that went to the rear, they went to the bumper of a reserve engine. So this whole thing is set up right in the mouth of one of the bay doors, overhead doors up. At the base of the door itself, there's a little lip, concrete lip. We use the flat foot option on the Vortex to bite into that lip. This allows us to swing this thing, starting if we want to go straight up in the air, all the way down to the ground, heading forward if we wanted to. And by tying off with those guy lines, we keep the rigidity of the entire assembly so that no matter where we pulled forces, that shouldn't sway. Kind of the idea was to sort of mimic the hydraulics when they're locked out and we have no unintentional moving parts. All forces were then loaded onto the change of direction. So where we had our load coming straight up, I think all of them, we had them so that our loads were straight plumb. That was an assumption that we made. We did not try to pull or kind of almost cross haul, if you will, but kind of pull a force towards the change of direction, then up. It was just straight down to the ground. And then we did different configurations with the multiple tests we did for where we put our anchors, the rope to an anchor and a device.
Yeah, so lastly, just some stuff on the Arizona Vortex. The Arizona Vortex only has a NFPA 1983/2500G rating, which is a minimum breaking strength of 32 kilonewtons in only two configurations. Those two configurations is a tripod, which all legs equal. So it would be like your confined space configuration, and an easel A-frame, still a tripod, but the back leg is longer. A sideways A-frame, regular A-frame, and a gin pole all fall under the technical rating of the NFPA standard. The rope that we used for our tiebacks is a high-strength, low-stretch cordage. Canyonator is the brand name that we used. And anytime you use a artificial high directional, I strongly encourage everybody to tie them off. It just increases the capabilities of an artificial high directional. Obviously, you can't tie off your aerial device, but if you do have one of these AHDs in your department, tying off is probably the best way to do it. To maximize the strength of the vortex, we minimized the height as much as we could for the testing that we did, and we minimized the length of the legs, and we didn't hobble it because you can't hobble a gin pull, and we went by all other manufacturer recommendations according to the CMC Arizona Vortex Manual. And if you're questioning what page that was in the Vortex Manual for gin pulls, it's page 22 in their CMC manual, which is essentially Rock Exotica's manual, because Rock Exotica makes the Vortex and CMC brands it as their own. So, all right, we can get into our findings, I guess.
Yeah, go right into it, starting with the first one.
So the first one, we did a monopod. So it's going to sound redundant because I'm just reading off our tests. Monopod with a remote anchor, 100-pound load. The angle of hoist, 68 degrees. So our monopod was lifted to 68 degrees, which is a typical angle for our aerial devices. And you're not going to see perfect angles like 65, 30. We hoisted it up, and then we took the angle after it was loaded, because yes, we're using low stretch rope, but there's still going to be some play in the monopod. So we want to make sure we got the true angle. So our math was correct, and all of our findings were where they should be. We did use a rudimentary protractor. We had
It worked, man.
It worked. Essentially, we didn't have a typical protractor. We took a T-square. We hung a plumb line off of it with a washer and read the angle that we got on our T-square. So, like I said, our angles are pretty close. You're not going to see dead like 65, 70. You're not going to see increments of 5. We just read the angles of where they fell, and that's what we recorded. So the angle hoist was 68 degrees. The change of direction angle, the inside change of direction angle was 35 degrees. So on a 100-pound load, the static load on that 35-degree change of direction was 180 pounds. And the max force it took, and this was a 1-to-1, I believe.
Yes.
We did not have a mechanical advantage in this. So we just hauled up on a 1-to-1, and we'll get into mechanical advantage at the end, and our findings that surprised me. But on a 1-to-1, the static pound force was 180 pounds, and the max pound force was 266 pounds. So right there, just hanging a load from a 68-degree angle on a rope system is almost increasing your poundage by 100%.
So I hope everybody understands what that interior angle means. So because this weight is plumb when it comes off the ground, it's straight down to earth. So you have a piece of rope, you have the section of rope that's going between the load and the change of direction, which is just a CMC, it's CMC pulley. We actually use a Prusik mining pulley, but the same thing. And then the other side of the rope as it passes between the pulley and where we had it remotely anchored, which was also the bumper. That's the interior angle. So between the two sides of its own rope. Okay. Between the head, the azorp, and the pulley, typically that would be your strap that would go to your tip, or whatever you use as your point of connection on your tip. That's it. In that place, instead of using a strap, we used the load cell enforcer, or an enforcer load cell, so that we could measure all of the forces that are being applied between the weight of the object and what we're pulling with, how it multiplies or adds together and puts that force directly on the tip. That was the goal of this thing. Yeah. So when you say that you have a static 180-pound force, we're reading it's the force that's now being applied directly to the tip from all the goofiness that we have going on below.
So at a 68-degree angle, we're increasing the load on the tip by 80 pounds. So a 100-pound load, we're getting another 80 pounds, an additional 80 pounds on that tip. NFPA says a single person load is 300 pounds. So if we're going to increase our load 80 pounds per 100, we've just increased our load by 240 pounds, which now is going to be about 540 pounds on that tip. And that's just a single person load at a 68-degree angle.
Not moving.
Not moving. And that's
just
not
dangling.
Right. And then max force is going to vary because the larger the load, the more force you have to apply on moving that load. I'm decent at math, but I can't figure out that math. That would be something that we would have to put a load cell on and pull, a 300-pound load to see what the max pound force on that enforcer would read. Okay.
The load cell was calibrated. It also was zeroed out each time, so we are not accidentally adding or incorporating some little ghost in the system. It starts with 0, then we apply the forces every single time. So just for everybody's clarification.
Okay, so we kept the same anchor, which was off the bumper, so it was a remote anchor. 100-pound load. Angle of hoist was lowered to 48 degrees. The interior angle at the change of direction was 80 degrees, so almost 90. The load cell readings, static load was 172, so we lost
8 pounds.
8 pounds.
Yeah.
8 pounds each. And the max pound force is down to 244. The one thing that we noticed on this was where our load cell was attached. It was the load cell was being torqued on the Azorp. So we conducted this test again. So when I saw those readings, I was like, those don't look right to me. So we changed where the Azorp was located so it was able to not be torqued. We moved the Azorp after this one, or we moved the load cell after this one so that Azorp or the load cell wasn't being torqued on the Azorp. What we figured is that it was reading a higher load than it should have because of the load cell wasn't free to move in space. It was being impinged by the lower ring on the Azorp.
Yeah, so instead of pulling end to end, like you're actually loading it, it was kind of almost being pulled end to end and slightly bent. So if you're trying to make this thing you're trying to bend it like in a U, it wasn't drastic, but it was enough that we thought that might benefit or at least warrant just moving over one hole in the Azorp so that we can clear that up.
But it's still, even with the torquing of the load cell, a lower angle of hoist, greater change of direction angle still lowered our pound force, static, and max. So
right. With this one, that's almost putting the resultant force directly in line with the gin pole or the monopod.
Correct. And if you're catching on what's going on here is most of the time when you look at your aerial, and we'll get into the inclinometers on aerial ladders compared to when you take a rope rescue class, the larger the interior angle, the change of direction, the less force on that change of direction. So the way to get a greater interior angle is to lower the aerial device as much as possible. The problem with that is now Matt and I were texting earlier, is you've created that lever action, and it's the fulcrum is at the turntable. And if you lower that lever, you're putting more forces on to the hydraulic system, on the lifting cylinders, or the hoisting cylinders, I should say. Lifting or hoisting. We're not talking about the extension cylinders. What people seem to think is when they raise their ladder up, they can get a better resultant force that's going down the aerial ladder. But what people don't realize is that those fly sections they're not all one unit. It's not like what we're using here with the Arizona Vortex, where everything's connected and pinned and slid into each other to create one solid piece of equipment. Your aerial ladder has fly sections, and those fly sections are held together by cables and pulleys and extension cylinders. And I don't know of an aerial manufacturer that does ladder testing where they take their extension cylinders and press them into a pressure plate. And what I'm talking is they take their aerial ladder and just extend it straight into a pressure plate until it fails, to know what the compression rating is on those extension cylinders, on the pulley and wire rope system, or even the aerial ladder itself. So firemen out there, they want to use, they're thinking like they're using a pterodactyl or Arizona Vortex system where they want these pulls and compression, but our aerial ladder is only tested and only meant to be used in a cantilevered fashion.
So kind of putting in words of a little bit more of a joking manner, but imagine you had the aerial bedded, but you were able to extend it straight out in front of you. All right, all the way. And then you drove it into a wall, right? How fast you got to be going, or how much force is it going to require for that thing to start collapsing down? It never tests in that direction. So when you raise the aerial, let's say it could go up, well, even if it held just even 80, like ours goes positive 80 degrees. You go 80 degrees up. If you have the ropes coming up the spine and then back down to the ground, it's almost 1-to-1, right? Because if it was straight vertical, 90, it was 100, like straight up in the air. Okay. And you had the rope going up to the change of direction and back down. The ropes themselves, there's the pound of force of the weight, then the pounds of force that you're pulling down on the other end. So that's doubling it. And that's going straight to the tip. So double that force, pushing, compressing the aerial flies, which that's why I make the joke. Like, it's no different than extending it straight out in front of you and driving into a wall.
Right.
It's not rated that way.
Until an aerial manufacturer gives me a ladder and I can put a pressure plate in front of it and extend that sucker out and see when it fails. This is the testing, and I'm not telling you not to use your aerial device. We're just trying to give you the information to make you a better rescuer out there and know what forces are being applied on your aerial. Test 3. This is when we adjusted the load cell so it wasn't getting torqued. Still a 100-pound load. The angle of hoist we raised up to was 80 degrees. Because it was still a remote angle, the interior angle at the change of direction was 70 degrees. The static pound force was, so the main thing to look at is, yes, the angle of hoist is changing, but the biggest thing is your interior angle on this one. And you'll see the differences when we change from the remote anchor to the base of the monopole, which most people, how they rig their aerials up for a rope system. They're not using a remote anchor like we're doing here. And that's why we change it up. But load cell readings, static pound force was 172, max pound force was 284. So we had an interior that's from the 80 degrees. It was the same static pound force as 70 degrees, but max pound force got raised. And we think that was the discrepancy due to the load cell getting pinged on the Azorb.
Right. And it's not much. It's not a terrible. It's not like, oh, Jesus, we added 100 pounds to it, but it was enough that when you do try to expand this out to the size of a ladder and larger weights, yeah, that could be significant enough to just throw you over the edge.
Yep. All right. So these are the ones that I paid more attention to, because this is when we changed our anchor to the base of the monopod. So if you look at some Instagram posts or social media posts, when they're using aerials as a high directional, they usually run their rope system up underneath the aerial through a change of direction and then to the rescue package. Depending on what they've used for anchor, they can use the jacking device. Maybe they have anchor points off the side of the rig. Whatever it is, what they do correctly, which should be common sense, is run the rope system in line with the aerial to reduce the torquing of the tip. You don't want your rope systems run along the side. So with the anchor set to the base of the monopod, the rope runs true, almost true, up the leg of the monopod until it gets to the change of direction pulley. It goes through the change of direction pulley, and then it's straight down from there. So still a 100-pound load. Angle of hoist was 78 degrees. The interior angle at the change of direction was 75 degrees.
I realize I think there's a small mistake when we were measuring our angles because of the way we were measuring with the thing that look at the interior angle of those two ropes.
Oh, you know what? Yeah.
It's 15 degrees.
15 degrees, yep.
15
I wrote that
right?
wrong, yeah.
Yeah, it's the complement to it. So we wrote 75. It's the way we were measuring off of. It's 15, so it's 90 minus 75. That's your 15.
Correct. It's a 15 interior angle, 15 degree interior angle. And like I said, if you want to get the pictures and the write-up we did from this, we'll get it to you. I got it saved on the computer, and we'll get them to you. That's a good catch. I didn't catch that on the initial write-up. So you can see our ropes are in line with the monopod. Load cell readings, here's where it gets interesting, and this is where people should pay attention to. The static pound force, so just hanging the load there, was 210 pounds. So
right.
it
We're not
doubled
quite
the weight.
Straight in the air, but we got this thing high and tight. So this would be the same as we're not extension. We're just raising this thing up damn near as high as it can go, like in raising motion, as high as it can go, so that I can run something up and back down to the ground, right? Just by connecting in and having this person, say, 1 foot off the ground, 100-pound little person, you're imparting 210 pounds at the tip.
That's just hanging there.
That's just hanging.
Not moving.
And that's a pretty basic setup.
Yep. And 78 degrees is not out of the realm for an aerial device.
Correct.
And to move this load, the max pound force it took for us, and this is still on a 1-to-1, the max pound force it took for us to move a 100-pound load through space was 460 pounds. So we multiplied our pounds 4.5%, or 4.5 times, not 4.5%, 4.5 times. So if we had just say, if you want to talk about NFPA and how they're NFPA, your max force might have to be greater to get them out because you've already doubled it. You're talking 1,000 pounds.
Yeah.
Almost. All right. So the next one, 100-pound load, angle of hoist 65 degrees, interior angle, that's going to be 30 degrees. Yep. Static pound force, 204 pounds. Max pound force is 246. So what we did is we lowered the ladder, or lowered our monopod angle from 78 degrees to 65 degrees, and we not drastically reduced the static pound force, but we drastically reduced the max pound force to move that load through space. 210 to 204 for static is negligible, but 460 to 246, we've reduced it by half. And I'm rounding.
Yeah, it's because of that one leg of the rope. As we're going from a vertical position and we're lowering this thing down, the closer we get to earth, the closer we get down to 0 degrees, so straight off the side of the rig, if you will, one of those sections is coming to 0. It's not going to be exactly 0, but it's coming to 0 because you don't no longer have just vertical. If it was straight up in the air, you'd have a vertical plus a vertical. Now you have a vertical, which is the distance between the segment that's between the change of direction and the load, and the other side of the rope is becoming more horizontal, so the load is measuring horizontally. So in terms of the load that's going to the tip, it's really only capturing the vertical loads.
So I think we should give full discretion on this one. Is that your previous job was an engineer, or you studied to be an engineer, and I was studying to be a physics school teacher, but partying and fraternity life got in the way of that. And so here I am as a captain at a firehouse.
Who knew you
So,
can put those things together and make a
right,
career out of it?
yeah. So what Matt is explaining here is if you go back to high school physics, and I know that's a long time for somebody, and if you remember going back to high school physics and you had to draw force vector lines and you had to add force vector lines and you had your X and Y, X is horizontal, Y is vertical. And if you had a force on an angle, you could add those. You could figure out what the horizontal force was and the vertical force was by just adding. You could convert each pound force to an inch. Each inch is 1 pound force, and so on and so forth. And you could figure out the horizontal force and the vertical force. I know we're probably getting the weeds with physics here. We probably lost everybody right now. But
And it's tough to do without an image. So we will put something up there so you guys go, oh, that's what they're talking about.
If you drew this up and you would fully understand. The big thing to take away is here is what a lot of people don't understand is that the more horizontal your ladder is, the less vertical force you're putting on that ladder, because the more horizontal it is, the more horizontal force in the rope system, the rope takes over the forces horizontally. The ladder only has to worry about the vertical. The people on the rope and the rope system and the anchor system has to worries about the horizontal force. All right. So go on to the next one. Yeah. So it was a 52-degree angle of hoist. Interior change of direction was 43 degrees. This is still on a 1-to-1. Static force is 204. Max force is 236, which correlates with what I was looking at with the 60-degree, the 65-degree. Just reducing the angle of hoist by, we'll say 10 degrees, lowered our pound force by, the static was the same, but the max pound force was lowered by 10. So just lowering the aerial device lowered our max pound force by 10. Yeah, so the 7 and 8, we moved the clutch to the top of the monopod. So it's interesting that the static force, even though we were only hanging 100 pounds off this, just the way how it was hanging, the static pound force still increased our load. Not drastically, but it was there, so we recorded it. So we hung the clutch just from the top of the tip of the monopod. So there was no change of direction angle. Load cell readings at a 52-degree angle was 112 static, 276 pound force. So just to yank this thing up on a 1-to-1, and when we pulled on the 1-to-1, we pulled in line with the gin pull, because that's how you would. We weren't pulling straight down,
which is 52 degrees away. So what essentially it's same concept as it's hanging. There's not two lines supporting the load, if you will. So it's that load should pretty much be going straight up to the tip, as if you tied a end-to-end piece of rope down to the load, and the other end is straight up at the top. That's what we did. Now add in, for the previous test, we had a change of direction in there. But imagine that thing could cam off or lock off, so it's only held up by one leg of the rope instead of both. That's why you're seeing the static at 112 pounds force.
The next one, we raised the angle of hoist to 70 degrees. Still no interior angle because the clutch was hanging from the tip. Static reading was 118, and the max pound force went up to 304 pounds. So we still 276 to 304. We're increasing our max force on that tip from 2.75 to almost 3 times the load from hauling on. It's still 1-to-1, but we're hauling through the clutch, which is on top of at the tip. We just want to see. That's really never going to happen. It's not how anybody's going to rig it. We just want to see what the numbers were. So we only did 2 tests. It kind of confirmed what we were thinking with the angle of hoist. And it's the greater the angle of the hoist. So the more vertical your ladder is, the more pound force you're going to put on your ladder.
As you're hoisting.
As you're hoisting. All right. So now we went into mechanical advantage systems. We did 3 tests. with mechanical advantage systems?
Let's see. This is the first one is going to be test 9. It was a 4-to-1 mechanical advantage system that we affixed to the top of the monopod. So we just tied it in. We had from the Azorp. Below that, we had the load cell. And then from the load cell down to the weight, we actually had a 4-to-1 mechanical advantage system. So this gave us no interior change of direction angle. The angle of hoist was 70 degree, 0 degree change of direction, and that gave us a load cell reading of static 118 pounds force and a max of 124 pound force. That meant that as we're hauling, it's essentially one strand of rope because we have no change of direction. We have it just running through the 4-to-1 mechanical advantage system.
So, as I was just saying, what I just said before, if you put in a mechanical advantage system, you drastically reduce the max pound forces implied on the aerial and the change of direction at the change of direction pulley. So, if we go back on the 1-to-1, where the interior angle, the angle of hoist was 78 degrees, which is close to 70 degrees. Our static pound force was 210 and our max pound force was 460. So we reduced our max pound force by 440 pounds almost, just over 440 pounds by integrating a mechanical advantage system.
Yes, and by integrating a mechanical advantage system, we're talking about, at least for this test, not at the anchor, then up to the change of direction. We've completely replaced that. So instead of a change of direction, we have a mechanical advantage system going straight down, kind of like what you would do with confined space, but we typically wouldn't be setting it up this way. This was just to prove a little math.
And we had a 5-to-1 mechanical advantage system.
Yep. 5-to-1 mechanical advantage system. So this is test 10. We took the mechanical advantage system. We went from the base of the monopod up to the change of direction, back down to the weight. So this is going back to a regular configuration, 100-pound load, angle of hoist 70 degrees, which gives us an interior change of direction angle of 20 degrees. Our load cell reading was static of 202, and our max was 254 pounds force.
Then on a 54 angle of hoist, the interior change of direction was 40 degrees. Static pound force was 190. The max pound force was 238. So essentially, the higher your aerial, the more vertical your aerial is, and if you're using ropes, depending on the rope system you imply onto it, you're going to be either increasing the load by 2.5 all the way up to 4 times the load. The lower your aerial is, you're going to be coming almost true. Theoretically, you're only going to have the weight of the load, the rescue package on that tip. Theoretically,
yeah.
So, where do we go from here?
Go into your conclusions a little bit. So you have your conclusion markers here, and I think pretty much you want to sum up what you kind of found here, or was that it?
I can read it verbatim.
Yeah, if you don't mind.
Summarize it. So I do have a kind of a note here. Using a mechanical advantage system reduces the amount of pound force implied on that artificial high directional at the change of direction. The reduction of force has a correlation with the angle of hoist. Now, if you were going to put your if you were going to run, and this only works if the mechanical advantage is in between the change of direction and your next anchor. If you run your rope system through a change of direction down to the rig through another change of direction and then remote anchor it somewhere else, and the mechanical advantage system runs between the second change of direction that's along the rig and your remote anchor, you're not going to get these reduction of forces.
No,
if that makes sense.
In fact, you're going to get a slight multiplication, right? So what you're kind of referencing to, and we looked at one this morning. You sent me one this morning the gentlemen that were in the video did that, and some of the departments I've worked with in the past have done this as well. So you have the load, the rope goes from the load up to the aerial, then change of direction down along the spine, typically underneath the aerial ladder itself, okay, to the side of the vehicle. So what's off the side of the vehicle? If you don't have an anchor point right there to tie into, if it's hanging off the left or right side, driver or passenger side of this thing, a lot of people will wrap the jacks and use that as an anchor point. And then they'll send it through a change of direction and then down the side of the road or down the side of the bridge, whatever they have to work with, right? We're talking about space and what's available to us. Each time you run it through a change of direction, you do add a little bit of a friction component, right? Just because it's a wheel doesn't mean that there's zero friction. That just doesn't happen. Most of them have a pretty good efficiency rating. But even if it's an 90% efficiency, you got to add the 10% cost to it on each turn. So to your point, if you run it through the change of direction up at the top, change of direction down on the side of the rig, and then away to the anchor, yeah, that's where you're going to see, you're not going to get those reductions because by the time you've gotten that, you've added a strength that you now have, a force that you now have to overcome.
Right. So the conclusion we had after conducting these tests is summarized that the angle of hoist, interior change of direction, and mechanical advantage all play no role in the forces applied to the artificial high directional at the change of direction. Unlike an aerial ladder, the Arizona Vortex is tested and configured to work in compression. Aerial ladders are tested to work in cantilevered. That is, the tubes of the Vortex are the strongest when compressed. The resultant angle when using an Arizona Vortex should be in line with the tubes or within that triangle when you hobble it or whatever. If anybody's taken an artificial high directional class, you know about the triangle with the hobble and everything else.
Inside the footprint, as they say.
Yeah, inside the footprint. This is not the way aerial ladders are configured. Aerial ladders are tested and configured to be used in cantilevered fashion, and aerial ladder manufacturers and third-party testers do not, nor do they have the capability to test an aerial ladder in compression. Like I said, if any aerial manufacturer that has the chance of listening to this podcast, if you want to reach out and you got a ladder out there and a pressure plate, let's go. Let's fail this thing.
So the physics of this, don't have to have a physics degree. Don't have to even do, high school physics to understand it. As a rope technician, so that's at your technician level. We all have like the awareness, the operations, and the tech level. The technician that's on scene there should be able to look at it and kind of understand the physics that are at play, the forces and everything that are generating between the haul team generating forces or the angles multiplying these forces. All right. You have two reference frames or two systems working here. You have the rope and interior angle, which create a resultant force, which is applied to the change of direction, i.e. the strap or that point of connection at the tip. Then you also have that same resultant force is now being applied directly to the tip, right? So the triangle of the rope that the rope creates generates a force that's going in the opposite direction. And then you have to figure out what that force is doing to the tip. Sounds complex, but really all you got to know is, hey, don't have this rope go straight up and then come straight down because that would be double. Now, the angle of the ladder that force is being applied is super important. Essentially, we need to know, are we generating a force that defeats that ladder? How do we know what our rating system is for our ladders? What do you got there?
So the only rating system we can go off of are the load charts that are in our aerial ladders. Actually, I saved it to this laptop. I think I was looking for pictures the other day. So do you remember when we had the old E1?
Mm-hmm.
Do you remember the inclinometer that was on the side of E1s, what it looked like?
It was actually a pretty massive chart.
So it had the plumb line in it, the little arrow that told you what angle you were at. And then it was like a 0 to 30, 30 to 60, and anything above 60, it gave little firemen like stick figures. They weren't really stick figures. It was like a circle head, fireman helmet, and triangle body. And it showed how many firemen could be on the aerial at that angle of hoist. And it didn't give any pounds for the firemen.
But I
All right.
believe at the time it was the ratings were supposed to mimic 250 a person type of thing for a safety margin.
Yeah.
So if you
So,
saw two people, two little firemen on there, that meant 500. If it was three, okay, now you're at 750, and so on and so
right,
forth.
right. We're always taught that from day one, working on an aerial, that you shouldn't have more than one person on the tip of the aerial at a time. Obviously, for you're rescuing somebody out of a burning building, we're gonna overcome that. And even when we're climbing an aerial, we tell people in our classes one person per fly. So if we have a 100 pound, 250 pound fireman, or even we'll just say a 200 pound fireman because we're supposed to be in shape. A 200 pound fireman at each section of the fly, and we're only allowed one fireman at the tip. That's 200 pounds at the tip. Aerial ladders, we were talking about this morning. Aerial ladders are either medium duty or heavy duty. Heavy duty aerial ladders, most of them are 750 pounds at the tip. There are some out there that are, the buckets that are 1,000 pounds at the tip. Some of the medium duty ladders are 500 pounds at the tip. I know for a fact an apartment in our county that bought a Pierce Ascendant that's, if it was normally rated at 750 pounds at the tip, they derated their ladder because they didn't want their jack spread so far.
Mm-hmm.
So they reduced the jack spread on their outriggers, but then the manufacturer wouldn't rate their ladder for the full 750. They only rated their ladder at 500 pounds. The other thing in discussion I had with an officer in this area, he's like, well, we're never going to overcome the safety factors that are built into the aerials. And my rebuttal to that is that the safety factors are there for the oh shit factor. I fucked up. Thank God the safety factor is built in. We should never be rigging something knowing that the safety factor is there so we can rig into the safety factor.
Right. And that's the difference of knowing what, your MBS, your max braking strength. So even on a carabiner, and then your working load limit.
And just for people's references, we looked it up today. The major truck manufacturers out there, Sutphen has a 3-to-1 safety factor. E1 has a 2.5-to-1 safety factor. Pierce is a 2.5-to-1 safety factor, and a Rosenbauer is a 2-to-1 safety factor. I didn't look up Ferrara. So everything's within the NFPA standard is a 2-to-1. Obviously, Sutphen went a little higher with a 3-to-1. That's just based on what they test their stuff at. That being said, and this is why I also explain when people say, well, the aerial, it's this big hunk of piece of metal. It looks super duper strong. I said, yeah, it's great, but what's your rope rated at? What's the NFPA? And I'm not talking what the manufacturer rating is. Just go, what is the NFPA rating for your rope?
Depends which one, but 6 to 9, somewhere in there.
What's the minimum breaking strength NFPA says your rope has to be? 9,000 pounds.
9,000.
9,000 pounds.
For a G rating.
For a G rating. What is a minimum breaking strength of carabiners? Depending on your carabiners, so we use steel carabiners, which are 52 kilonewtons times 220, and I'm building in a safety factor there. Those carabiners are rated at just 10,000 pounds right there. So our ropes are at 9,000 pounds. Our carabiners are at, we'll just say 10,000 pounds.
10,000.
The next, and we just switched our software over to Dyneema runners and Texora slings. How much are those Texora slings rated at?
The max braking is from end to end 100 kilonewtons.
100 kilonewtons. Okay, 100 kilonewtons. 100 times 220. It's a whole lot of pounds.
Yeah,
You're not breaking that. The point I made and I make to people that want to use an aerial device is that you're putting your weakest tested piece of equipment at the highest point that can have the most catastrophic failure before anything else. Your rope's rated at 9,000 pounds. Your carabiners are rated at 10,000 pounds. Your clutch is a G rated piece of equipment. Our anchor slings are rated way above our even rope strength right now. Even just a simple, an old school prusik minding CMC or even an SMC pulley, those were 26 kilonewtons pulled on each side. That's at 5,720 pounds. So in the rope rescue realm, when you're doing rope rescue, everybody says the first thing that's going to fail is the pulley because that's the weakest link in the system. The pulley is at almost 6,000 pounds. They're probably even more right now. Those Omni blocks, I don't have the rating off the top of my head right now, but I was going off of old school technology that I know the old prusik mining 2-inch pulleys were 26 kilonewtons on each side. That's 6,000 pounds. Even if your aerial ladder is 1,000-pound tip with a 3-to-1 safety factor, you hit 3,000 pounds.
Right.
That's failing before your pulleys. So what is the benefit besides convenience of using your aerial device, which is these aerial devices are going for $2 million now to run a rope rescue system through it, where that is the piece of equipment that's going to fail first.
Right, and just break. And we can't even account for hydraulic failure or something of that nature. And you think that, hey, hydraulics, they have freaking how many freaking ton-pound ratings to them, but if it's just that one bad day, it's not like there's a pin in place that locks out that cylinder to keep it from moving.
Right. So can you use an aerial for rope rescue? If you're going to run a rope system through it, and use it as a traditional high point, I would be very hesitant to do it. Does it look freaking awesome for social media?
Oh, hell yeah.
Yeah, it does. But I think the better option, and I talked about this with the truck boss that works on the tower on my group, is our better option is to rig a set of fours from the tip of the aerial to the rescue package and use the aerial ladder as a hoisting device. And everybody is like, well, you're not supposed to use it as a crane. It's like, we're not using it as a crane. So a crane, we're not extending, we're not retracting. All we're doing is lifting and rotating. And by slinging the tip and putting a set of fours off that sling on the tip down to the rescue package onto and at that point, you know what your load is.
Right. It's the weight of the person.
It's the weight of the person plus the victim. And even if you retract the ladder, they're still not in any danger because that tip is not going to get fully retracted into the other fly sections. Your tip still sticks out a couple rungs.
Mm-hmm.
So theoretically, we can swing our aerial ladder over to the side, rig up a anchor sling off the tip of the ladder, put a set of fours off that sling to the Stokes basket or whatever rescue package you use, put an attendant on that basket, and use the aerial ladder to lift, rotate, and set them down on wherever we need to rescue this person from an elevated platform is. They can put that victim into the Stokes basket, package them up, and God forbid they need medical assistance while maybe they need airway, maybe they need to be bagged, something's going on. Because we know the weight of the rescue package, which is going to be the attendant and the victim, that load doesn't change because it's directly in line. It's tied to the tip. There's no rope system. And the reason why we have that set of fours is because they can load up the system themselves and then adjust instead of having the aerial raise up and then the attendant's like, oh, my harness is all messed up. He can raise up the package off the ground and get adjusted where he wants to. And then the aerial operator can raise, lower the victim package down. I know
Right.
this goes against everything a lot of people have heard before. CMC did a podcast, I don't know, maybe 2 years ago on this. And one of the guys actually recommend. I think it was almost like an on the spot recommendation. Like it was like almost like an epiphany he came to that was the way it should be done. And thinking about it, it's probably the safest way to do it because you're not changing the loads through a change of direction. It's directly tied to the tip,
Right.
and
So
it's
it's just
simple.
straight. The weight coming down is what you're getting at the tip.
And it's simple.
So what's interesting about that argument? Because yeah, a lot of people are going to hear that and freak out because we're talking about below the platform or below the tip. All right. But we're not running lines through a change of direction, so there's no multiplication. So now it comes down to you're dangling somebody with no ability to move. Now with a set of fours you can adjust, but it's really not movement. So you can adjust. And if you raise, move, rotate, and lower, that's kind of what it sounds like a crane. Okay, now you have, hey, you're not supposed to apply mechanical devices, powered mechanical devices to something that has a live load on it, right? Okay, I can understand that. They're talking in terms of like a winch or using an ATV that you're, imagine something's tied to the back of the ATV going down over the edge and you just drive away from the edge so that it raises a victim, right? You don't know if they snag on a rock. And that's kind of where that came from originally. But take a look at another thing. Like I said, it's everything's below the tip or below the platform. But most of these platforms, they have those swing out arms that you mount a Stokes basket to. So you have an attendant, but in this case, they're not really an attendant. They're just a fireman and a tip. And then you have a Stokes basket mounted to the front of this bucket with a victim inside of it. So it's not impossible because these things are rated in one thing. Now what we're doing is instead of putting it on the arms, we're just hanging them by a rope underneath. How is that different?
Right. So I found the picture, and it's actually, it's awesome how I found this picture. When we sold our old E1 Cyclone, and it was up for sale on one of the consignment fire truck sites, I found it, and they had the chief at the time took a picture of the turntable, and I was able to zoom in
perfect.
on the load ratings, the load capacity of the aerial. So E1 says each fireman is 250 pounds. Obviously, hopefully we're in shape. And during rope rescue, we're not in turnout gear. But for the sake of the argument, E1 has each person's 250 pounds. So and obviously we're not flowing water in rope rescue, so I'm just going to go off of the non when
The dry
there's no
weight.
the dry waterway. So I'm looking at this at the ladder operation tip load only from 8 degrees from that might be a negative 8 degrees to 40 degrees. The tip load is 2 people, so it's saying 500 pounds.
No extension, or is that with extension?
It doesn't,
Because there's isn't there 3 waves under it that kind of says how
it
far?
doesn't say extension. So it goes into there's another line here for more people, but this is just tip loads.
Okay.
So if you're just putting people on the tip from negative 8 to 40 degrees, you can have 2 people on the tip, so it's rated at 500 pounds. What you have to think about, though, is we just said you don't want to put 2 people on rope because we're increasing our load. The more horizontal we are, it's so hard to comprehend because the aerial ladder wants you to work vertically, because when we're working vertically and there's people on the ladder, the forces implied on that ladder are transmitted down the aerial ladder, which reduces the amount of cantilevered force.
Which it's tested for.
So on the tip load for, like I said before, negative 8 to 40 degrees, 2 people, and then from 41 to 76, we go 3 people. So this aerial ladder was rated at 750 pounds total. Okay. That's still less than the 800 pounds of max force we can be implying on these systems. So if we put more people on this ladder and we want to evenly distribute the people on the flies, so if we extend this ladder out and we're going to climb this, so if we have 3 people on this ladder from -8 to 30 degrees, we can have 3 people on this ladder, but they have to be equally distributed and only one person on the tip. From 31 to 45 degrees, we can have 5 people on the ladder, but only one person on the tip. And then from 46 to 76 degrees, we can have 8 people on the ladder and still only one person on the tip.
And again, that's because it's not applying a force into its actual rate, right? It's kind of showing you the negative space here.
Well, the one thing what I took away from that was that those last ratings I gave were when the load was equally distributed. If I were to use the aerial, if I had to use the aerial as a high directional, I would not extend the aerial out, and I would only wrap the bed section of the aerial ladder.
Right.
I wouldn't wrap the tip. I'd wrap the bed section, because even on our ladder, on our 107 Ascendant, the bed section, if you notice on our load charts, is always 1,000 pounds.
Mm-hmm.
It's the tip that's 750, and the tip never changes. So I don't know what the engineering went into that, but the tip is always 750. But that bed section is 1,000 pounds almost all the way through your operation.
Right.
So if I had to use that aerial as an artificial high directional, the bed section is the best, safest spot to use as your change of direction. The problem is you're not getting the height that you need with it.
Unless it's something like out over the side of a bridge.
Right. In the video we saw, I mean, they were using, what do they call it, a reverse skate block?
The one you sent me.
Yeah.
Yeah, so this company, I'm not sure where they were. I didn't even look them up. It was a fire department. They had a tiller. They took the aerial off the side, driver's side, angled it up. I don't remember what the initial angle was, angle of inclination. But what they did is they ran a line underneath the aerial up to the tip. And then the tip was extended just over a roof line. So what they were trying to do is they wanted to raise the package, the rescue package, up, and then have it be able to swing out and over a roof. So what they used was a skate block. Skate block being, for those that don't know, you're essentially riding your own line up on an angle, and then you disconnect or lower out and away so that you go back plumb. So you ride up, you are not plumb.
So and
that's what they were trying to do. Is you have that adjustability to ride the skate block and then reduce it out to plumb.
And skate blocks are great, but what I looked at when I looked at that aerial ladder, that interior angle at the change of direction,
you're double.
It was 90 degrees,
right?
Because
when it was done, yes.
Because he was,
but don't forget
because he was tight raising, to the rope, right?
Yeah, exactly.
So he's doubling his load immediately on that tip of the aerial
for the ride up.
For the ride up, he might have been a 180-pound dude, and we're putting 360 pounds on that tip immediately. Now it's below the rating, and what they did say is, in their configuration, that the rescuer didn't ride down with the victim package. They were going to use a tagline, but when you tag that victim package off the side of the building, you're changing that interior angle again. It's making the interior angle of that change of direction smaller, which is increasing your load package on the tip.
Correct.
So
they're good and bad.
Yeah.
And I like using the skate blocks because they're kind of fun, and it feels like magic, because when you're raising it, everything kind of rides one direction, and when you're lowering, it seems like it swings. The load lowers in a different spot than it does when it raises, even though you did not change anything. So it's kind of it's fun to operate with. However, the most important thing I think it is a great takeaway from using these high directionals with aerials is exactly what you just stated before. Is okay, you had a rescuer or attendant on that basket going up. There was no patient because the patient was on the roof. When they packaged the patient, the attendant disconnected and they waited up top. So just the package came down with a patient. And that's kind of where you're going to get into, hey, good, better, best type of, tiered steps. That middle ground where it's okay, it's if you're going to go high angle, way out, whatever, try to reduce your weight inside that package. And that would be don't ride the basket and a patient at the same time. Have somebody disconnect, but consider what it is you're landing on top of. A rooftop, a flat rooftop, not a problem. If it's a ledge, like a gorge ledge that's up in the air instead of coming down to the gorge ledge, that could be problematic because you are disconnecting from your safety and now you have nothing to tie to. Right? Unless there's some sort of like hard anchor that you can come up with, but these are things you got to think about.
But like with slinging the tip of the aerial and running your set of fours from that sling to the directly to the victim package, and then using your aerial as your moving device, you can still load the aerial with your attendant and victim.
Yes, yeah. Because you're not doubling the forces.
Because when we do rope rescue here, who's a person going on rope? Usually, it's one of the it's not always the most qualified, because you really want the most qualified person, depending on the what we're doing, up top, making sure the rigging is correct. So usually we pick somebody that has rope rescue certifications, and then I look around who's the smallest dude, because I don't want to be hoisting up the biggest dude there is on the job. I don't want to take my retired driver that's sitting in Florida right now. God bless him. He was one of the best guys that could rig, but he was not going on rope. He knows that. He'll listen to this, and I'll get a text message saying, "Hey, don't make fun of me," and I'm still going to make fun of him. But he's not going on rope. I'm looking at, the guy that's 150 pounds soaking wet. I'm going to throw him in a harness. So now I know my rescuer load is 150 pounds. Even if we have the 400-pound biker dude that got stranded somewhere, he's an HVAC tech on his daytime job, and he has a medical emergency. We have no rooftop access. We have to use the aerial ladder to get him down. 400 pounds plus 150. We're at 550 pounds. My aerial is rated at 750. If I directly connect them into the tip of the ladder, I'm never going to over exceed the rating of that ladder. As soon as I run a rope system through there, all bets are off. Depending on the angle and the mechanical advantage system we use and where our anchors are, we're going to be applying forces on our aerial that we don't know unless we put a load cell into that system. And as of right now, that load cell doesn't have a remote app that I can look on my phone where I can be on the hard deck, making sure my loads are within the ratings of that ladder. It'd be nice, but they're not there.
Yeah, even if you had a 30-degree inclination, you'd have to be way away from a building just to get the rise.
Right.
To get something to rig, doing a crane operation. And how high is it? Remember when, it wasn't your group, was it, that off the bus garage roof?
That was us, yeah.
That was you? Did you guys rig something like that, or did you do the old ladder?
No, we just lowered them on a normal rope system. We anchored to an HVAC unit that was on top of the roof.
The one currently being repaired?
Is it getting repaired?
Yeah, like sometimes maybe it's not wise to just go right for the high point because you just did the training last week, or that's the most recent thing. Think of some other things. I like that. You take the straight ladder. You could use an extension ladder, but a straight ladder is probably the best. It pivots off the corner of the building in the ground, and you just let it lower out. Right. So the Stokes basket kind of comes off the roof, ends up laying on the ladder, and That's pretty sweet setup as well.
Yeah, I think it was either like the first video I saw on that was either like a month before we had that rescue, or maybe a month after we had that rescue. So we didn't really train on that, and we just we were still using racks and
Oh yeah, this was a long time ago.
yeah, we were still using J racks and tandem Prussic belays for that job, and went fine. We loaded them up, we put them over the edge, lowered them down, and we had two guys tag them because there was a couple gutters that the scuttles off the flat roof that were in the way, so we didn't want the basket hanging up on that. They tagged them off the roof and lowered them down. Right, I think we lowered them right onto the stretcher.
Oh, perfect.
Yeah.
So
But
many options here.
I mean, and that was the thing. Could we have used an aerial for that? Yeah, but we needed to get this guy off the roof that was having a medical emergency. By the time we rigged up that aerial and everything, how bad could it have gotten? Could he have coded on top of the roof at that point? It was quicker for us to anchor off the HVAC unit. Now, would I anchor off an HVAC unit now from the knowledge that I've gained from a captain that used to work on HVAC units? I probably won't anchor to an HVAC unit unless it's like dire needs. Because if you know anything about people that work in HVAC, the boxes that those things sit on are usually scrap pieces of wood that they find left over at the end of the day. They build up that box with whatever scrap wood they find. They build the box up, they set the HVAC unit on it. So they're not really that secure into the roof, and they tar over it. It looks nice, and we're good to go. Did it fail? No. Did it work? Yes. I probably would have anchored to something else in that scenario, looking back on it. But the point is that we did a basic rope rescue. We climbed a ground ladder, got up there, assessed the patient. I think he was having an MI. We put him in the Stokes basket, lashed him up, put the bridle on, lowered him down. All said and done, it was very basic, very basic.
That was fast too.
I saw some posts of some tech rescue teams doing twin tension systems over the side of the aerial, and they put their load cells on the anchors, and so you're not getting any true readings of what forces are being applied on the aerial device if your load cell's on the anchor.
No, you're just getting the weight that what is it called? Not
Transmitted,
but yeah, just transmits through the wire essentially.
right?
You're getting the same picture from end to end, but you're not seeing the what you're imparting on the tip, and that's where the load cells should be. But now you got to get a guy up there as well, which, okay, he's looking straight down. He's standing on the tip, looking straight down on this load cell and going, yeah, you're still good. You got 80 more pounds, right?
Yeah, but
not realizing he's 200 pounds sitting on that tip as well.
Right. It would be nice to make a load cell that has Bluetooth capabilities that's remote, that I can read off a tablet or a phone.
There's got to be one, is there not?
You know what? Our load cell probably does. I probably got to pay for an app. I don't know. I haven't looked into it. I know there's Bluetooth. There's a Bluetooth thing on it, but I don't know what app I need for it to read. It's probably something I should look into. And if that's the case, if we have that load cell with Bluetooth capabilities, it might not be a bad idea to have it on the rig for scenarios like that where you had to use it. And that's the other thing. I can't think of many places that we would need an aerial as an artificial high directional.
At least not in our jurisdiction at this point.
I mean, it really anywhere. I mean, the biggest fire department in the world, the FDNY. I follow them on Instagram. I get the International Association of Fire Chiefs newsletter. If they've done a rope rescue off an aerial, it hasn't come across any of my news feeds.
Yeah, I can't think of one.
And they do some serious rope rescues. I mean, I don't know. like I said in the beginning, until an aerial manufacturer gives me a ladder and we can pressure test that and extend that into a pressure plate and figure out when that aerial fails in compression, maybe I'll change my tune. If that aerial fails in compression at our pulleys are failing at 5,000 pounds. So if that aerial ladder fails at 5,000 pounds, okay, I'll change.
Right.
But right
And in the
now,
meantime, you got to be smart about how you're multiplying these forces. One, you got to recognize that there is a multiplication if you're using a change of direction.
Right now, the aerial ladders are rated between 500 and 1,000 pounds, depending on your aerial ladder. That's the only information we have on our aerial ladders is that rating. And through our testing, we have proven that you can far exceed those ratings depending on the change of direction that you've implied on that high directional. So do what you want. If you guys want to contact us for the write-up, I'll change the angle so they're correct.
Any closing arguments? Anything you want to
I think I've said my piece with the aerial devices. My recommendation, I'm just a captain. I've messed around with these ropes for a while. It looks cool to do these rope rescue systems through your aerial device. It might not be the best solution there is. I think the best, safest solution is to sling that tip or sling wherever you're going to sling that you need. Run a 4-to-1 from that sling directly to the victim package or to the rescue package, and then use your aerial as your moving device. Because carefully, slowly,
get plenty of eyes on it. Yeah, exactly. That's going to be the key, the clutch to that thing. We're not saying go out there, change your SOGs, SOPs, and do this instead. It's just be smart. Try to figure out the math on paper in practice first before you have to go out there and do this stuff. Oh, we heard Matt and Lou talk about this. We can totally do this. Try and understand the numbers, or at least understand using like the little arrow methods and everything, where those resultant forces are and how they kind of multiply. You don't have to get a direct decimal, down to the degree like we do, but just understand that, hey, the closer that ladder is going out off the side of the rig, so essentially it's flat, perpendicular with the ground, or parallel with the ground, the lower amount of force you're imparting on the tip. The higher it is straight up in the air, the more you're getting as well.
We had a DM from one of the people that follow us on Instagram. They wanted us to, because we're in the Northeast, they're in the Carolinas, and they don't get the cold weather like we do. I mean, they do get frost and, freezing temperatures. They're just not familiar with, some cold weather procedures, how we operate the fire trucks in the cold, what we have to do, some of the preparations we take. So we're getting notes and some stuff compiled for an episode on that. We're still trying to hammer down a date for two of our buddies that went through a Mayday in their volley department. We have the audio. Actually, he gave me his write-up on it that he did for the volley department, kind of like an after-action report on it. We're trying to get them hammered down, but the chief he's getting married, so he's going to be out of town for the next 2 weeks.
I believe he's getting married out of the country.
Yeah, so out of town. So
he's far out.
Yeah. We still got to do that question and answer episode. You got questions kind of compiled. So yep. So we got a couple episodes in the hopper, even though we can't hammer down the two guys that went through a Mayday, and we're still actively reaching out to people around here. We got turned down by one of the guys here. He's like, I'm not a good public speaker. You don't need to be a good public speaker. We just need your knowledge on the engine shit. So that being said, thanks for listening, share, follow, spread the word. That's all I got.
Yeah. Hit that subscribe or the follow on Spotify, Apple Podcast. I think it is on Audacity now.
Odyssey, not Audacity.
What it is, the audacity of a man. Odyssey. Yeah, I did see it on there. when you hit that, at least it kind of branches out, lets more people know that this thing's there, and the more people we can piss off, the more people this generates some conversation with, and that gets people leveling out, and we like to see that. Not so much do we like to cause controversy; it's just we like the information, and it needs to keep moving.
Yep.
So reach out to us. firefrom2windows@gmail.com is how you can reach us with the email. You got the Instagram handle out there. That's Fire from Two Windows, all one word. It's TWO, not the number 2, for both of them. And I think that's it, right?
That's it.
All right. Until next time, stay safe.
I guess it.